Okay, so now we're going to be getting into the introduction of mechanisms and specifically thinking about linkage mechanisms. And so we're really going to define what are different types of links, different types of joints that you'll be using, and then getting into how do I actually sketch these in a common language for the kinematics field. So starting off, a mechanism is a device for transferring force and or motion between an input and an output. And so when you think about this, you can say, well, there's lots of different ways that I could do this. I could do it with a linkage mechanism, which is a main focus of this class. But I could do it with a cam mechanism, as you see in many internal combustion engines. I could do it with gears, whether or not they're simple gear trains or planetary gear trains, which we'll talk about later in the class. So lots of different types of mechanisms. The focus of the first half of the class will be on linkage mechanisms. So the definition of a linkage is just simply rigid links that are connected by joints to form kinematic chains. So a bunch of words there. So rigid links, if I'm looking at this skid steer loader, which can move this loader up and down and tip the bucket as I break the bucket off, this has a series of rigid links. They are connected by joints, both pin joints and these hydraulic cylinders, which are sliding joints. And that forms a kinematic chain. This happens to be a closed kinematic chain. So one thing I need to mention as I'm talking about chains is that this one being a closed chain, meaning that we're starting at the frame, coming back to the frame, that's a closed chain. But if I'm thinking about something like a robot manipulator, many of these are open chains. So I'm thinking about, hey, I've got a shoulder joint here which has 3 degrees of freedom. I've got an elbow joint with another degree of freedom. And this, my hand, my end effector, does not come back to the frame itself. And if it did, then that would be a closed chain. Otherwise, we're looking at open chains. So my caution here, not all linkages are mechanisms. So we're talking about rigid links connected by joints, but not all of them are mobile. And so if you think about kind of more like a truss structure, where I've got maybe a ground pivot here, I've got a link with a pivot and another pin, which is then connected to another ground pivot, something like that, that would be a linkage that is not mobile and therefore not a mechanism. So just be careful that truss structures are not mobile, whereas if I took this same idea and said, hey, let me add one more link to it, so I've got ground connecting up to a point here, another link that I'll call a coupler link, and then connecting down to another ground pivot. Now this is what we refer to as a 4-bar linkage. We've got ground as 1, 2, 3, 4, and now this has mobility. You can imagine I can grab one of those links, start rotating it, and it would move the rest of the mechanism. So again, just be careful there between, not all linkages are mechanisms. So let's now start talking about this common language that we use to describe a mechanism, or specifically a linkage mechanism. So we're going to do a kinematic drawing of this skid steer loader and look at what the different links and joint types are in this. So I'm going to start off by just taking this skid steer and now identifying all of the ground links, all ground pivots, I should say, as well as all of the other links in the device. So starting off, I'm going to look at the frame of the vehicle, and so I've got a connection right here, which is ground. I've got a connection right here, that's ground, that's the bottom of that hydraulic cylinder, and I have another connection over here. So those three together form my ground, or the frame of the vehicle. Now, a kinematic drawing, you simply create lines between all of your joints. So I've got a joint here at the back side of the skid steer loader. I'll draw a line up to this pivot up here, and I'll put a circle at the pivot. So that tells me I've got a pin joint, and that's the starting of my kinematic diagram. I can do the same thing at my other joints on the loader arm. So I've got all of these joints right here, a joint out here at a hydraulic cylinder, and a joint at the tipping of the bucket. And now as I start to sketch these other links, I've got a connection between the front bottom part of the frame of the vehicle and that loader arm. So this coming up here, so just a straight line between those. I've got a hydraulic cylinder, and the way I draw a hydraulic cylinder is that I have something that looks like the cylinder rod connected down here, and I usually add these little lines right here that tell me that has no rotation between those. And then I put my piston rod, which then connects up to that point there. So now we're saying that's able to slide relative to the other end of the hydraulic cylinder. I then get out to the bucket, and you'll notice there is another pivot here on the bucket. I will sketch the bucket kind of with some extension out here that kind of gives me some feeling of what the space is that it occupies, just because that's my end effector and what I'm most likely interested in. And then what's controlling the rotation of the bucket is another hydraulic cylinder that's kind of buried back in here. I will draw it something similar to the previous one. I've got my piston rod, which then connects down to that point there. So those are the primary links, and then I need to create one big link for the loader arm itself. So all I have to do is connect all of these pivots, and this then becomes my kinematic diagram for this 4-bar. Sometimes I'll, shade it in some form just to allow us to see, okay, that's all one part of the link, and similarly with the bucket. So that would now be the starting of my kinematic drawing. So let me fade away the picture of the skid steer loader, and now you can see my 2-year-old drawing. Looks like it, but this is now a little bit easier to look at and start to analyze and say, hey, where are all these connections? What types of joints do I have? I've got pin joints, I've got slider joints. This is now the common language that we use to start our analysis and even a lot of our synthesis. So a few things before we call this a completed kinematic drawing. First is that I am going to number all of my links, and then I will letter all of my joints. So that'll be our labeling system. We always start off with ground as link 1, so I will put 1 next to all of my ground pivots. And alternatively, I could connect them if I wanted to, but I'll just label them all as 1. And then I can really arbitrarily go around the rest of the linkage and label it as I wish. So I'll call this link 2, I'll call this one link 3, I'll call the big coupler or the loader arm link 4, and then I'll do 5 and 6 to the 2 pieces of the cylinder here. I'll call the bucket link 7, and then this side of the cylinder I'll call link 8, and this side of the cylinder I'll call link 9. So this happens to be a 9-bar linkage. Now similarly, I'm going to label all my joints. So again, it's really arbitrary where I want to start, but I'm going to start at A here, B, C, D, E is this pin joint down here. F is the slider joint right there, so that'll be the slide. G will be up at this location. A, B, C, D, F, G. H will do down here. I will be this pin joint. K will be the cylinder. And then we'll do L up here. So quite a few joints in this loader mechanism. So now I've completed what I call a completed kinematic diagram of the vehicle, labeled all of the links with numbers and all the joints with letters. The next thing I do is I say, well, it's a 9-bar linkage, and then I start to say, well, how many joints does each one of the links have? And that then defines whether or not there's a binary link or a ternary link and so forth. So a binary link is a link that has 2 joints on it. So the majority of the links in this case, link 2, link 3, link 5 and 6, those are all binary links, as is link 7, 8, and 9. Link 4 happens to have how many connections? I've got 1, 2, 3 on the left side, 4, 5 on the right side. So that happens to be a pentagonal link. So we just define these based on how many links or how many joints they have. So binary, ternary, quaternary, pentagonal, and hexagonal links. All right, moving on, let's talk more about the different types of joints that I can have. So in the planar world, meaning all in one plane, even though this skid steer might have left and right sides, but in one plane, as I represent a mechanism, I usually start off with pin joints and slider joints. So if I've got a pin joint that is grounded, I would usually sketch it as I was just doing over there, where I've got something like this that is grounded, and if I happen to have a moving pin joint, I can place another one up here, and then that would be a moving pin joint that's saying I'm allowing rotation there and I'm allowing rotation here. What we then start to say is, how many degrees of freedom does this joint remove? And then this gets us to talking about mobility. So if I look at the number of degrees of freedom that are removed by each type of joint, you'll note that if I'm talking in a planar world, I have motion in the X direction and the Y direction as well as rotation, so I have 3 degrees of freedom. And a pin joint removes one of them. Or I'm sorry, removes 2 of them and allows just rotation. So I'm going to remove 2 of 3 degrees of freedom. So I'm removing the X and Y and only allowing rotation. Now when I move to a slider joint, if I have a slider on ground, I sketch my ground looking like this, and I've got a slider block that is able to move back and forth relative to it. An assumption that's made with this diagram is that this slider block will not lift off. So assume that it's captured somehow, even though I've only drawn one side of it. So again, This now removes rotation as well as my motion in the y direction as I've drawn it here. So this will remove 2 of 3 degrees of freedom. And you saw just a moment ago me sketching this as a hydraulic cylinder for a rotating slider joint, and that's how you would treat that. How about a roll slide pair? A roll slide pair can look like a cam that's moving, a sliding follower. It can look like a car tire on the ice in Minnesota where that tire is either rolling or perhaps sliding if it's slipping on the ice. Or it could look like something like a pin in a slot. So imagine that I have a link that has a fork joint that looks like that, and then some sort of a pin that's inside of there that's connected to another link, and that's allowed to both rotate as well as translate back and forth down that slot or that fork. So this joint allows rotation as well as translation in one direction, so it's removing 1 of the 3 degrees of freedom. So note that I can have different joints that have different reductions in the number of degrees of freedom. And then the other joint types that I have on here are getting into spatial mechanisms where I can have a helix or something like a screw where I'm combining both the rotation and the translation, removing a number of degrees of freedom. A cylindrical joint where I'm allowing something to translate and rotate. A spherical joint like my shoulder that has 3 rotational degrees of freedom. And then a planar joint thinking about something sitting on a plane where I allow x, y, as well as rotation about that plane. So we won't talk too much about those, but want you to be aware of those types of joints.